Alright guys, in this video I'm going to go through everything that you need to remember for AS Physical Chemistry. Before we get started, I do want to mention that I am now offering one-to-one remote tutoring, so if that's something that you'd be interested in, message me on Instagram, which I'll link down below. Okay, so we're going to get started with the structure of the atom. So our positive particles are protons, and our negative particles are electrons. And our neutral particles are neutrons. So here we have what we see when we look at the periodic table, right? So we see the element and two different numbers. So our small number we call the atomic number, and this number basically just tells us how many protons there are and how many electrons there are in a neutral atom. And then the big number we call the mass number, and this tells us how many protons and neutrons there are. Okay, so here we have our charges and the masses. So the charge of the proton is +1, neutron is 0, and electron is -1. And then the masses are 1, 1, and 1 over 1800. And then the definitions. So the relative atomic mass is the average mass of an atom, of an element, compared to 1/12 of the mass of a carbon atom. And then the relative molecular mass is the average mass of a molecule compared to 1/12 of the mass of a carbon atom. And then the relative isotopic mass is the specific mass of an atom of an isotope compared to 1/12 of the mass of a carbon atom. And then here we have two different isotopes of chlorine, chlorine 35 and chlorine 37. So those specific masses are the relative isotopic masses, and then if we work out the average, that's the relative atomic mass. And to work out the average, we do the sum of the mass numbers times the abundance, all divided by the sum of the abundance. Okay. So now to actually work out what the different abundances are of the isotopes, we use time of flight mass spectrometry. So you need to know all the stages for this. So the first stage is ionization, and there's two different types of ionization. So one is when high energy electrons knock off electrons of the molecule, and this is called electron impact, and this forms X+ ions. And then the next type is electrospray, and this forms XH+ ions. So this is when a sample is dissolved and sprayed through a needle with high voltage, forming XH+ ions. And then the next step is acceleration. So this is when the ions are accelerated to the same kinetic energy by an electrical field. And then the next stage is ion drift. So this is when the ions travel through a vacuum. During this stage, the lighter ions will move faster. And then the last step is detection. So the ions will hit the detector plate and accept an electron, and this generates a current which is proportional to abundance. Okay, and the MZ values are what you see on the computer. And when you use electron impact ionization, the MZ value will be equal to the mass. However, when you use electrospray ionization, the MZ value, well, you gain a proton using electrospray, so your mass goes up by 1. So the MZ value will be the mass of your molecule plus 1. However, also, if you use electron impact ionization, sometimes you can knock off 2 electrons by accident, and then you're doing your mass divided by your charge. So your charge is now 2, so it's mass divided by 2. So another MZ value can be mass divided by 2 if you knock off 2 electrons. Okay, most of the time it will just be mass. Okay, So for the maths questions involving time of flight spectrometry, you need to know these three different formulas. So the kinetic energy is equal to a half mv squared. The velocity is equal to distance over time. And the mass of the ion is equal to the relative atomic mass divided by Avogadro's constant, and then divided by another 1000 to get it into kilograms. Okay. Now for questions with two isotopes, you need to calculate the time taken for one isotope to travel through the spectrometer and use this to calculate the time taken for the other isotope. So to do this, we use the fact that the kinetic energies are equal to each other, and then we get this formula. And then with that, you can just sub in your other formulas, so like velocity is equal to distance divided by time, and all these other ones. Okay. And then next we have the orbitals. So each shell can be split into a subshell, and each subshell can be split into orbitals. The s subshell has one orbital, so 2 electrons. The p subshell has 3 orbitals, so 6 electrons. The d subshell has 5 orbitals, so 10 electrons. And the f subshell has 7 orbitals, so 14 electrons. The s subshell has a spherical shape, and the way I remember this is s for spherical, so s for the s orbital, and then the p orbital is just the other one, and this shape has a dumbbell. Okay, so just remember s for spherical, and then the next one is dumbbell. So when we actually write down the electron configurations, the big number represents the energy level, and then the letter represents the subshell, and then the small number represents the number of electrons. So this is the order of the energy levels up to 4p. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. Okay, so I'm going to do an example of nickel. So we typically just fill up all the energy levels in this order until we reach the number of electrons we have. So we have 28 electrons. So I'm going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then next we have the 3d. So we have 8 electrons left, so I just fill it up to 3d8. Even though d can fill up to 10 electrons, we only have 8 electrons left, so I'm just going to fill it up to 8. Okay, so now we're asked for the shorthand configuration of nickel. So for this, we look at the noble gas right before nickel, which is argon, and we can use argon to summarize all of this. So then we just say AR, 4s2, 3d8. These are our exceptions, okay? So chromium and copper are 2 exceptions. So the structure of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5, okay? So the weird exception is that normally we would fill this up to 4s2, but instead one of those electrons that would normally go to 4s2 goes to 3d5. And then copper, same thing, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then 3d10, okay? So once again, we don't fill up 4s, we just go straight from 4s1 to 3d. Next, we're going to focus on the spin diagrams. So for fluorine, first I'm going to write down the electron configuration, so I know how many electrons go in each orbital. So fluorine is 1s2, 2s2, 2p6, okay, sorry, no, 2p5. So now when I'm writing down the when I'm writing down the spin diagrams, I'm going to do 2 electrons in the 1s, and then we've got 2s2, and then 2p5. So I'm going to write down 3 orbitals because p has 3 orbitals, and I've got 2p5, right? So when I have orbitals at the same energy, the way you fill it up is you fill them up singly first, so like this, and then you start to pair them up. Okay. Next we've got the ionization energies. So the way I think of the definition is I like to write down the equation first. So the general equation for ionization energy looks like this. For the actual definition, I like to write down the equation to then work out the definition. So the X ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous X-1 ions / atoms to form 1 mole of gaseous ions. Okay, and these ions have an X charge. When you have X-1 is equal to 0, you get atoms because the charge, if the charge is 0, then it's neutral, so it's an atom. For any other instance though, if it's +1, +2, +3, then you use the word ions. Okay, so X-1 when it equals to 0, that's the only instance when you use the word atoms. Now the factors that affect ionization energy. So when the nuclear charge increases, the ionization energy increases as well. However, when the atomic radius increases, the ionization energy decreases, and when shielding increases, the ionization energy decreases as well. Here I've got a graph of all the different electrons being removed. So this represents when you remove the first one, then the second, then the third, then the fourth. So the first ionization energy is lowest, and then it generally goes up, and this is because atomic radius decreases as we remove more. Here though, there's a big jump. Okay, and the main reason for this big jump is that we move to a more inner shell, and that means that there's 4 electrons on the outside. Okay, so that means we're in group 4. So this can help us locate or identify what atom we have. Okay, next we have all of these, which are the first ionization energies of period 3. So as you can see, once again, there's a general trend upwards, and this is because as we go across a period, the nuclear charge increases and the atom gets smaller. However, there are 2 drops. So there's 1 drop here and 1 drop here. So the drop from magnesium to aluminium, which is group 2 to group 3, can be explained since we're removing from a higher energy level. So from an S to a P. And then the drop from group 5 to group 6, which is phosphorus to sulfur, is because the repulsion between delocalized electrons in the same orbital. So what that means is, if I draw down the orbitals for phosphorus, so this is the highest energy level for phosphorus, right? However, for sulfur, we have 1 extra electron. So this extra electron creates repulsion in this orbital. Alright, now we're going to move on to amount of substance. So we're going to focus on moles first. When we have 1 mole of something, that means you have 6.022 times 10 to the power of 23 particles of that substance. If you have 1 mole of a substance, then its mass in grams is the same as its MR. And this gives us the formulas that the mass is equal to the moles times the MR. and then the number of particles is equal to the moles times Avogadro's constant. And then we have this formula for the ideal gas equation that pressure times volume is equal to moles, which is given by N, R, and T, which is temperature. And the volume is in meters cubed, and the temperature is in Kelvin. And to go from degrees Celsius to Kelvin, we add 273. The concentration in moles per decimeter cubed is moles divided by volume in decimeters cubed. The density is equal to the mass in grams divided by the volume in centimeters cubed. Make sure that you look at the units they want to use the same units in your calculation. To work out the empirical and molecular formula, firstly you divide each mass or percentage by their AR, and then you divide all of these answers by the smallest answer. And then to find the molecular formula, you need to multiply all the atoms in the empirical formula by this fraction here, which is the MR of the molecular formula divided by the MR of the empirical formula. So here we've got an example. A compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen. It has an MR of 180. Find its empirical and molecular formula. So firstly I'm going to write down all the atoms involved: carbon, hydrogen, and oxygen. So carbon is 40%, hydrogen is 6.7%, and the oxygen is 53.3%. Then I'm going to divide them by their ARs. So we get 12, 1, and 16. And then this gives us a ratio of 3.33, 6.7, and 3.33. And then we can simplify this ratio by dividing by the smallest number, which in this case is 3.33. And we get 1, 2, and 1. So the empirical formula is CH2O, and the MR of this is 30, and we need this MR to work out the molecular formula. So to work it out, we do 180 divided by 30, and we get 6. And then we do the empirical formula, which is CH2O times by 6, and we get C6H12O6. So that's our molecular formula. I like to think of water of crystallization as a bit of like a sponge. So imagine having a water-soaked sponge and heating up the sponge to evaporate all the water. The aim is to find out how much water you originally had inside the sponge. So to do this, I've given an example first for us to actually understand it. So we have 3.51 grams of zinc sulfate hydrated, and this was heated to 1.97 grams of zinc sulfate, and then there's going to be some water remaining as well. So firstly I'm going to write down the equation that we get, which is and then basically this bit here is kind of like our water soaked sponge, and this is the dry sponge on its own. So originally the sponge and the water combined are 3.51 grams, and then the dry sponge on its own is 1.97 grams. And we can work out the mass of the water by subtracting 3.51 by 1.97, and we get 1.54. And then I'm going to divide all of the masses by the MRs. So we get 161.5 and 18. And when I do this, I get 0.0122 and 0.085. And this is the ratios. And then I'm going to divide both of these ratios by the smallest number, kind of like empirical formula, so that I get and when I work this out, I get 1 and 7. And so this one here represents the one before the zinc sulfate, and then this 7 here represents the number before the water. So this lets us know that X is equal to 7. Okay, so when you add distilled water to a solution, the concentration of the solution changes, and we can use this formula for this, which is old concentration times the old volume is equal to the new concentration times the new volume. Okay, so just remember, old equals new. Also, just to be clear, the new volume means the old volume plus additional volume, so the volume that you added. Okay, 1 mole of any gas at 25 degrees and 100 kilopascals has a volume of 24 decimeters cubed. Under constant temperature and pressure, you can use volumes instead of moles. So what this means is, if you have the balance equation and you can work out the mole to mole ratio, then you can use these mole to mole ratios with the volumes. So here we have 2, 2, and 2 for these reactions and reactants and products. So that means that the volume of this will be the same as the volume here. So then this is 500 centimeters cubed, and then this is a 2 to 1 ratio. So then we do 500 divided by 2 and we get 250 centimeters cubed for this. Then here for percentage yield, we do the actual yield divided by the theoretical yield times 100. For the percentage atom economy, we do the MR of useful product divided by total MR of product times 100. The percentage uncertainty is given by the formula uncertainty times the number of readings. All divided by the measurement times 100. And then the uncertainty of an equipment is half of the smallest increment. A titration is when you mix a solution of known concentration, which we call the standard solution, with a solution of unknown concentration. And the whole reason we do this is to find out the concentration of the unknown solution. So here I've got an example for us to try. 25 centimeters cubed of hydrochloric acid is reacted with 22.4 centimeters cubed of 2 moles per decimeter cubed NaOH. Calculate the concentration of hydrochloric acid. So I've got the balance equation here for us to use, which is really useful. And I like to set up my these types of questions like this, where I have the moles, concentration, and volume. And then I write down all the stuff that we know. So we know we have 25 centimeters cubed of HCl, which I convert to decimeters cubed. And then we know we have 22.4 centimeters cubed of NaOH, which is this in decimeters cubed. And then we know we have 2 moles per decimeter cubed of NaOH. So now we can do concentration times volume to work out moles. So then we have this many moles of NaOH. And then, since it's a 1-to-1 ratio between hydrochloric acid and NaOH, we just let the moles of hydrochloric acid be 0.048 as well. and then we do the moles divided by the volume again, and we get that the concentration of hydrochloric acid is 1.792. A back titration is when you have a sample of something that you want to test it for its purity or percentage by mass of a certain substance or something else. So in order to work out the purity or whatever, we mix the sample with water in a volumetric flask, so with those big flasks, and this big solution that we have is our unknown concentration. So we take a small sample out of this big flask and we titrate it with a standard solution. Okay, so that's basically just a normal titration calculation. So in order to answer the calculations involving a back titration, we need to work backwards from the practical. So firstly, we work out the moles of the unknown concentration in the titration. Then we work out the moles of the unknown moles in the volumetric flask. So that big flask, how many moles of your sample were in that? And then the last step is always kind of different. So it might be to work out the percentage by purity, percentage by mass. It might be to work out some value of X. Okay, it might be to work out the MR. So it's always different. Okay. So in this example here, we're told that 3.96 grams of M2CO3 was dissolved in distilled water to make 250 centimeters cubed of solution. 25 centimeters cubed of this was titrated with 32.8 centimeters cubed of 0.175 moles per decimeter cubed of hydrochloric acid. Calculate the MR of M2CO3. So essentially, this bit here is when they make the big solution in the volumetric flask. Okay, so that big flask. And then this bit here is when they get a small sample from that big flask and they titrate it. Okay, so we're going to work backwards. So the first thing we do is the titration. So just like before, I like to answer my titration questions with N, C, and V. And then I write down all the information that we know before. So we know that we have 25 centimeters cubed of M2CO3, which is equal to 0.025 decimeters cubed, and then we have 32.8 centimeters cubed of hydrochloric acid, so that's 0.0328, and then our concentration is 0.175, so this gives us 0.0057 moles by doing concentration times volume. And then from the molar ratios, I can just do 0.00574 divided by 2, and I get that the moles of M2CO3 is 0.00287. Okay, so now I know how many moles are in 25 centimeters cubed, right? However, in that big flask, we had 250 centimeters cubed. So to go from 25 to 250, I times by 10. So I can do that with the same for the moles. So I do 0.00287 times 10, and I get 0.0287 moles. So now we know that in 3.96 grams of M2CO3, we have 0.0287 moles. So that means I can just do mass divided by MR to work out mass divided by moles to work out the MR, and I get that the MR is 138. Now let's move on to bonding. So the first part of bonding are the different types that you can get. So first is ionic bonding, which is a strong electrostatic force of attraction between oppositely charged ions. So we're asked to find the formula of magnesium chloride. Firstly, I'm going to write down the ions that we form. So magnesium is in group 2, so it loses 2 electrons to have a full outer shell. And chlorine is in group 7, so it gains an electron to form a full outer shell. And then I'm going to write down the atoms involved, so Mg and Cl. And basically we just swap these charges down, so this 2 comes down here and this 1 comes to the magnesium, so we get MgCl2. Next we're asked to draw the dot and cross diagram for calcium oxide. So calcium is in group 2, so it loses 2 electrons to gain a full outer shell, and because of this it gains a 2+ charge. And then oxygen is in group 6, so it gains a full shell by gaining 2 electrons, and then these are the 2 electrons that it gains from calcium, and has a charge of 2-. The melting points of ionic structures increase as the ionic radius decreases and charges increase. Metallic bonding is an electrostatic force of attraction between metal cations and delocalized electrons. So if we're asked to draw the structure of magnesium, we have big positive metal ions, and then we have electrons floating about, and these are all delocalized, so they don't belong to any certain atom. And then we have more positive metal ions. Right, so melting points for metallic structures increase as the number of electrons increase and the ionic radius decrease. Alright, so covalent bonding is a shared pair of electrons between atoms. To draw the cross and dot diagram for methane, I'm going to start off with a central atom, which is carbon. And then I'm going to draw all the electrons. So carbon's in group 4, so it has 4 outer electrons. And then it's bonded to hydrogen 4 times, so I'm going to draw 4 hydrogen atoms around it and label them H. And then hydrogen donates an electron to each covalent bond, and I'm going to mark that electron with an X. Coordinate bonding is a shared pair of electrons with both electrons being supplied by one atom. So if we were to draw NH4, we would draw the N, and well, we have ammonia, and then we have H+, which has 0 electrons, right? And nitrogen has a lone pair. So what happens is that this lone pair donates both of its electrons to the H+. When we're asked to draw a dative covalent structure or a coordinate bonding structure, we don't need to draw the lone pair. So I'm just going to rub that out. And also, the charge becomes sort of delocalized, so it spreads across the whole molecule. Okay, so this arrow here shows that both of the electrons are being supplied from the nitrogen. A normal line like this shows that 1 electron is being supplied from each atom. Macromolecular structures are giant covalent structures. Okay, so for the melting points, metallic structures have a high melting point, simple covalent have a low melting point, macromolecular have a high, and ionic structures have a high melting point and boiling point. The conductivities of all of these structures, well, for the conductivity you need a delocalized charged particle. So metallic structures have a delocalized electrons, so it's good. Simple covalent don't, so it's bad. Macromoleculars typically don't, so that's bad as well. And ionic structures are good when molten. or liquids. Okay, electronegativity is the ability of an atom to attract the pair of electrons in a covalent bond. Electronegativity increases as atomic radius decreases, shielding decreases, and nuclear charge increases. A polar covalent bond forms when the atoms have different electronegativities. A polar bond has an uneven distribution of electrons in the bond, forming slight charges. For symmetrical molecules, the dipoles cancel out. The molecule is non-polar. Ice has more hydrogen bonds than water. These bonds cause the molecules in ice to be further apart than in water, making it less dense than water. Okay, so we'll talk about what hydrogen bonds are later. But first, van der Waals forces occur when you have an uneven distribution of electrons, causing a temporary dipole. This induces a dipole to neighboring molecules, leading to an attraction between slightly negative on one molecule and a slightly positive on another. So what this means is, if we have a molecule like this, for example, this is one molecule, and it will just have electrons floating about randomly in the molecule, and these electrons can float about anywhere, right? However, just by chance, what can happen is that all of the electrons are on one side of the molecule, okay, and this is just by luck, okay, and for this split second, the right side of the molecule will be slightly negative and the left side will be slightly positive. And what this does is it causes the electrons here, which once again are all floating about randomly, these electrons are all repelled to the right side. So now this molecule has an uneven distribution of electrons. So now this molecule is slightly negative on the right side and slightly positive on the left side. So then the slightly negative of this molecule is attracted to the slightly positive of this molecule on the right. So then this here is the van der Waals force. And this occurs for all molecules. A permanent dipole-dipole force is the difference in electronegativity leads to bond polarity, and there is an attraction between the slightly positive on one molecule and the slightly negative on another. So basically, if we have two atoms, so say carbon and chlorine, one of the atoms will be more electronegative. So in this case, chlorine is more electronegative. So then the electrons will shift more towards chlorine. So for example, here you have more electrons on the right side. And then it's the same thing for this molecule. So say it's CCl, the electrons will be shifted more towards the right. And then we have slightly negative here, slightly positive here. And then same thing here, slightly negative, slightly positive. And so the main difference is that this is permanent, okay? Whereas here, this was for a split second. This one's permanent. And once again, the slightly negative on this molecule will be attracted to the slightly positive on the other molecule. And this occurs in molecules with a permanent dipole. And finally, we have hydrogen bonding, which occurs when there is a larger difference in electronegativity negativity between hydrogen and X. Okay, so X is a general atom, and a slightly positive and slightly negative dipole is created, and there's attraction formed between the slightly positive H plus and the lone pair on X. Okay, so X can be nitrogen, oxygen, or fluorine, which I've said here. Okay, and here we've got an example. So with these molecules, the dipoles will look like this. And then I'm going to draw the lone pair on the right molecule. Oxygen has 2 lone pairs actually, so it looks like this. And then this negative lone pair is attracted to the hydrogen. Alright, and so the H plus has to be directly bonded to one of these atoms: nitrogen, oxygen, or fluorine. For their strengths, the hydrogen bonding is the strongest, and then van der Waals is the weakest. Okay, and finally we have the structures of all these compounds. So to work out the structures, first we draw the displayed formula, and then we count the amount of bond areas. And then to work out the electron pairs, we do the group number of the central atom plus the number of bonds, take away the charge, all divided by 2. Right, and then to work out the lone pairs, we do the electron pairs minus the number of bonds. Alright, so here I've got, actually this should be bonding areas. Okay, so we'll go through what that means in a bit, but these are all the different types of structures you can have. So when you have 2 bonding areas and 0 lone pairs, so all of these molecules here have 0 lone pairs. Okay, so these are your basic structures, and to remember the names, I've drawn the angles as well, because that kind of helps us remember the names sometimes. So 2,0 is called linear, and you can remember this as it has a 108-degree bond angle, and linear means straight, right? Which also has any straight line has a 180-degree angle. And then the next one, 3,0, is called trigonal planar. Planar just means flat. And then we have 4,0, so that's tetrahedral. And tetra means 4. And then we have trigonal bipyramidal. Okay, so tri and bi, so we have 3 plus 2, which equals 5. And then 6,0 is called octahedral. And here we have all the shapes with lone pairs. Okay, so the way I remember this is, remember firstly these numbers, they're quite easy to remember: 2, 1, 2, 2, 3, 1, 3, 2, 4, 1, 4, 2. And then there's 2 special numbers, so 2, 3 and 5, 1. Okay, and then remember this BLTS, so like a BLT sandwich. And the way you fill this out, bent for both of these. And then this next one's linear. This one's trigonal pyramidal. And then here, this one's T-shape. Then here, 4-1 is seesaw. 4-2 is square planar. And 5-1 is square pyramidal. Okay, and these are all the different bond angles involved with the shapes. So here I've got an example for us to try. So draw the shape of NH4+. So firstly, I'm gonna draw the displayed formula, which looks like this: N, H, 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 and then we've got this arrow here. That doesn't really matter when we're talking about how the structure looks, okay? And it's got a positive charge. And then, so we know that, as we can see, it has 4 different bond areas, right? So BA equals 4. The number of electron pairs is equal to, so the group number of the central atom, which is nitrogen, and that's 5, plus the number of bonds, so there's 4 bonds, and then you take away the charge, so the charge is positive 1, so you take 1 away, and you divide all of this by 2, and we get 4 electron pairs, okay? And then, so our total number of electron pairs is 4, but if we want to find out the number of lone pairs, we do 4 minus the number of bonds, which is 4, and we get 0. So we for BA and LP, we get 4, 0. So now if we compare that to what we have here, 4, 0 is a tetrahedral, and that's what a tetrahedral looks like. So tetrahedral, and we have N, H, 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 and one last H, and then to draw the positive charge like that, okay? And then if you want, you can also just draw the arrow if you want to show the coordinate bond. Reactions can either be endothermic or exothermic. So if your reaction is exothermic, it means that the products have less energy than the reactants. And then if your reaction is endothermic, it means that the products have more energy than the reactants, so it takes in energy. Now we can mark the enthalpy change by marking the energy difference between the reactants and the products. Okay. And then the activation energy is the energy difference between the reactants and the maximum amount of energy. So that looks something like this. So we'll talk more about what activation energy is in the next chapter, but enthalpy change is the heat energy change measured under conditions of constant pressure, and the units are kilojoules per mole. When you have this symbol over here, that just means understanding the conditions, which are 298 Kelvin and 100 kilopascals. Okay, so the enthalpy of combustion is the enthalpy change that occurs when 1 mole of a substance is completely burnt and oxygen at 298 Kelvin and 100 kilopascals with all the reactants and products in their standard states. So for methane, the reaction for the enthalpy of combustion is 1 mole of methane, which reacts with oxygen, and that forms CO2 and H2O. So methane is a gas for its standard state, and then oxygen is a gas as well, carbon dioxide is a gas, and water is a liquid, and then we just need to balance it out. Right, now incomplete combustion is less exothermic than complete combustion, and incomplete combustion is basically when there's not enough oxygen for all of the fuel to react. Enthalpy of formation is the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard states at 298 Kelvin and 100 kilopascals. The enthalpy of formation of an element is 0. So for methane, the reaction for the enthalpy of formation is, well, we're forming methane, and it's a gas, and its elements are carbon and hydrogen, and hydrogen is a gas, and carbon is a solid, and then to balance this out we put a 2 in front of the hydrogen. Okay, Hess's law states that the total enthalpy change for a reaction is independent of the route taken. Now, when we draw the Hess's law cycles for combustion and formation, for combustion we draw the arrows down like this. Okay, and I remember this as like CD, and then formation is upwards, so FU. So here's an example to try. So work out the enthalpy of combustion of propene. So they've given us the formation values, so we know that the arrows are going to be pointing up. So if I write down the balance equation, we get this. And then its elements are carbon, hydrogen, and oxygen. So to form propene, we take in 20 joules of energy, and then for carbon dioxide, we release 394 joules of energy. However, we do this 3 times, so we times it by 3. And then for water, same thing again. So we release 242 joules of energy, but then we do this 3 times. Okay, so if we want to go from the left side here to the right side, like this reaction is, we need to go downwards this way and then upwards this way. So when we go downwards, we go against this arrow here. So in our calculation, we'll flip the sign, so we get minus 20 instead. And then when we go along here, we're going along with the arrow, so we keep the signs the same. And we get minus 1928. Now we're asked to work out the enthalpy of formation of propene. So the reaction for this looks like right, and the atoms are carbon and hydrogen. So when we combust carbon, we give out 393 joules of energy. And we do this 3 times. And then when we combust hydrogen, we give out 286 joules of energy, and we do this 3 times as well. And then propene, when we combust it, we give out minus 2058 joules of energy. Oh, sorry, I forgot a negative sign over here as well. So when we go from left to right like this reaction, we need to follow this arrow here. So we keep the signs the same for the left side for these values, and then we go upwards here. So we go against the arrow, so then we flip the sign over here. So we get 21 kilojoules per mole. Okay, next we have this formula, Q equals mct, change in T. Q is the energy, which is in joules. M is the mass, which is in grams. And the change in temperature is in Kelvin, typically, but it can be in Kelvin or degrees. It doesn't really make a difference. And then the enthalpy change is equal to Q divided by 1000 to get into kilojoules, and then divided by the moles. So one experiment that we have is where we have a solid and a solution, or we have 2 solutions, and these are mixed in a well insulated cup, and the temperature change is measured to calculate the enthalpy change. Okay, so all solutions are assumed to have the same density and specific heat capacity. As water. So here there's an example for us to try. Calculate the enthalpy change when 25 centimeters cubed of 0.2 moles per decimeter cubed of copper sulfate reacts with 0.01 moles of zinc. The temperature increase is 7 degrees. So firstly we're going to work out Q, which is, well, we have 25 centimeters cubed, and we can assume that it has the same density of water, which is just 1. So we can assume the mass is 25 grams, times by the specific heat capacity of water, which is 4.18, times by 7 for the change in temperature, and that gets us 731.5 joules. And then I'm going to work out the moles. So we do the volume, which is 25, divided by 1000, times by 0.2, and we get 0.005 moles. And then to work out the enthalpy change, I'm going to do 731.5 divided by 1000, all divided by the moles, so 0.005, and I get 146 kilojoules per mole. Okay. However, this is an exothermic reaction, so we know that it's going to be a negative sign in front of the value. So our final answer is minus 146 kilojoules per mole. And here we've got another example. So 25 centimeters cubed of 2 moles per decimeter cubed hydrochloric acid reacts with 25 centimeters cubed of 2 moles per decimeter cubed of sodium hydroxide. The temperature increase was 13.5 degrees. Calculate the enthalpy change per mole of hydrochloric acid. So once again, if you work out Q, now in this case we have 2 different solutions, right? So we include the masses of both. So here we have 25, and then here we have another 25. We'll assume that the densities of both is 1. So then altogether they weigh 50 grams. So 50 times 4.18 for the specific heat capacity of water, times by 13.5 gets us 2,821.5 joules. And then moles, well, since we're doing it per mole of hydrochloric acid, we work out the moles of hydrochloric acid, so that's 25 divided by 1000 times by 2, and that gets us 0.05 moles. Then to work out the enthalpy change, we do 2821.5 divided by 1000 to get into kilojoules, and then divide it by the moles, and we get 56.4 kilojoules per mole. But once again, the temperature change is an increase, so we know it's exothermic, therefore the value is going to be negative, so we add a negative sign. Next we have the mean bond energy. So this is the energy needed to break the covalent bond into gaseous atoms, and this is averaged over different molecules. So mean bond energies are always positive since you're breaking a bond, and well, if you want to work out the enthalpy change from the mean bond energies, we do the sum of the bonds broken minus the sum of the bonds made. Enthalpy change values calculated using this method will be less accurate than using formation or combustion data because mean bond energies are not exact. Okay, and then here I've got a final type of enthalpy change question to try out. So these types normally come up as 1 markers. So the way to go about it is, firstly, look at the reaction that they want you to work out and compare it to the reactions that they've given you. So in the final reaction we have Fe2O3 as a product, so that's the first thing that I look at. And here, this is the only thing that has Fe2O3, so we know that this reaction, and it's in the product side, right? So it's in the right direction. Also, we have 1 mole of Fe2O3 and we have 1 more here. So this reaction is perfect, okay? That's correct. This one, however, well, we have FeO in the product side. However, on this side, we for this final equation, we have FeO on the reactants. So firstly, what I know is that we're going to have to switch this. Okay, so I'm going to rewrite it in the other direction. So we get FeO solid to half O2 and Fe solid, and then the enthalpy change for this reaction would be positive 272. And then in the final reaction we have 2 moles of FeO, whereas in this reaction we only have 1 mole. So I'm going to times this by 2 so that we get okay, and I'm just going to bring this one down actually so that we can add it to the other equation. So this is our top reaction here, okay, just written in a different way, and then here I'm going to bring that down as well so that we get okay. Now if I add these 2 equations together, what's going to happen is that this 2Fe is going to cancel out with this 2Fe, and then here we have oxygen on the left side and oxygen here on the right side. So 1 O2 is going to cancel out, so we get alright, and this looks exactly like our reaction here that we were given. So now I just need to add up these values to work out the enthalpy change, and I get alright, so that's that question done. Alright, so Connect is quite straightforward in my opinion. So reactions can only occur when collisions take place between particles which have the correct orientation and at least the activation energy. So the activation energy is the minimum amount of energy the particles must have to react. If we have something like an exothermic reaction that we just did before, looks like this. Activation energy is the energy from the reactants to the maximum energy, and we can just call that EA. Here we have a Maxwell-Boltzmann distribution. So this top energy is called the EMP, and then to the right of the EMP is the mean energy, and then here is the activation energy. So the EMP is the most probable energy. Okay, and only a few particles have at least the activation energy. So if you see here, if you look at the size of the whole graph, okay, and all the area underneath it, only this many particles have the activation energy. Okay, mean energy is always to the right of EMP. As you can see, the line goes through the origin, and this is because 0 particles have 0 energy, and the area under the graph represents the total number of particles. Right. Okay, so if we increase temperature, the Maxwell-Boltzmann distribution shifts to the right a bit and down. Okay. And what this does, well, if we write the activation energy like this, so the total area is unchanged. Okay, so that's because the number of particles hasn't changed, right? However, if we increase the temperature, this leads to an increase of kinetic energy of the particles, and this causes the particles to move faster, resulting in more frequent successful collisions. Okay, also the increase of kinetic energy means a higher proportion of the particles have at least activation energy when they collide. So the rate of reaction is equal to the change in concentration of a substance in unit time, and the units for concentration is usually moles per decimeter cubed. So for a graph of concentration versus time, the gradient represents the rate. So here, for example, we have a curved line for concentration against time. So to work out the gradient, we draw a tangent, and then we work out the gradient of this tangent. Okay, so for this reaction here, we usually measure rate as 1 over time, and t is equal to the time for the cross to disappear due to the cloudiness of sulfur. If we increase the concentration or the pressure, basically you're increasing the number of particles, so you're increasing the area. So the whole graph will go up like this. And then as you can see, if we draw EA, there are more particles now on the right side of EA. So more particles have at least activation energy. So if we increase concentration or pressure, this leads to an increase particles per unit volume, and so the particles collide more frequently, leading to more frequent successful collisions. So in this case, the shape of the curve is unchanged. The curve goes up because there are more particles. Increasing the surface area will cause successful collisions to occur more frequently. Increasing the rate of reaction. Okay, so catalysts increase the rate of reaction without getting used up. And they do this by providing an alternative route with a lower activation energy. So here, if we have the energy profile diagram, the activation energy is the energy difference here. However, with a catalyst, the activation energy would decrease like that. So the activation energy with the catalyst is lower. And for the Maxwell-Boltzmann distribution, what a catalyst does is this shifts the activation energy to the left. Nothing else has changed. Alright, moving on to equilibrium and Kc. This arrow here shows that the reaction is reversible. At dynamic equilibrium, the forward and backward reactions occur at equal rates. And also, the concentrations of the reactants and products stay constant. If the position of equilibrium is towards the left, the mixture will contain mostly reactants. Le Chatelier's principle states that if an external condition is changed, the equilibrium will shift to oppose this change. If temperature is increased, the equilibrium will shift to oppose this and move in the endothermic direction. To try to reduce the temperature. By absorbing heat. Increasing pressure will cause the equilibrium to shift towards the side with fewer moles of gas. To oppose the change, and thereby reduce the pressure, if the number of moles of gas is the same on both sides, then changing pressure will have no effect on the position of equilibrium. Increasing the concentration of a substance on one side of the equation causes equilibrium to shift to the opposite side to decrease the concentration of the substance to its original concentration. A catalyst has no effect on the position of equilibrium, but will speed up the rate at which the equilibrium is reached. A factor could increase the yield of the substance you're trying to prioritize. However, it may also increase costs and or decrease rate. Therefore, a compromise is made between yield, rate and costs. The Kc expression for this reaction would be alright, so you do the products over the reactants, and then you have your actual substance inside the brackets, and then you have your mole number as the power. So for the units, we do the moles on the right hand side minus the moles on the left hand side, and then we let that equal to x, and then we do moles per decimeter cubed all to the power of x. So here's an example for us to try. Okay, so in the ice table, we know that we're going to gain for the products and we're going to lose for the reactants. Okay, so for hydrochloric acid, we went from 0 to 0.2, so we gained 0.2 moles. And hydrochloric acid has a 2:1 ratio with chlorine. So if we gain 0.2 moles of hydrochloric acid, we're going to lose 0.1 moles. And the same thing with hydrogen. So then we're left with 0.4 moles of hydrogen and 0.5 moles of chlorine. And then we do all of these moles here divided by the volume to work out the equilibrium concentrations, and we get now I'm going to write down the Kc expression for this reaction, which is and now I'm going to sub in the values, and I get and my final answer is 0.196. And as for the units, well, we do the moles on the right hand side, which is 2, minus the amount of moles on the left hand side, which is 1 plus 1, so 2 as well. So we do 2 minus 2, and we get x is equal to 0. So then we do moles per decimeter cubed to the power of 0, and that gets us no units. So Kc is equal to 0.196, no units. Here's a little quick tip for you guys. When the moles on the left hand side equals the moles on the right hand side, you can sub in moles instead of concentration into the Kc expression. So in this example here, we have 2 moles on the right hand side and 2 moles on the left hand side altogether. So when we were subbing in the concentrations here, we could have just subbed in these moles here instead. Okay, and that's only because we have the same amount of moles on the right hand side as we do on the left hand side. Okay. Alright, here we're asked to work out the Kc for the opposite reaction. So for this, all we need to do is 1 over the original Kc reaction, which was 0.196, and we get 5.102. And then once again, we have 2 moles on the right hand side, 2 moles on the left hand side, so we take them away, we get 0, so we get no units. The larger the value of Kc, the more the reactions will favor the products, and Kc only varies with the temperature. Alright, so here's a question involving some algebra. Hydrogen and bromine form hydrogen bromide. 0.2 moles of hydrogen and 0.2 moles of bromine are mixed and allowed to reach the equilibrium, and the Kc value of this is 0.210. Alright, so it seems that I've left a bit out. Basically, we just need to work out the moles of hydrogen bromide at equilibrium. Alright, so to do this, I'm going to rewrite the reaction and write down the ice table. And we have 0.2 moles of hydrogen and 0.2 moles of bromine. They haven't mentioned hydrogen bromide, so we can just assume that it's going to be 0. And for the losses and gains, we can just use a general variable like x. So let's say we lose x moles here, then because it's a 1:1 ratio, we're also going to lose x moles here. And since it's a 1:2 ratio, we're going to gain 2 moles here. Alright, so then at equilibrium, this is the moles that we have. Alright, now when we're forming the Kc expression, Kc does obviously include the concentrations. However, like we said before, since we have 2 moles on either side of the equation, we can just sub in the moles instead of concentration, which is why I haven't written down a volume in the question. So we can just do Kc is equal to HBr squared over H2 times Br2, and then instead of subbing in concentration we just sub in moles, so we get and we can simplify this to and we know the value of Kc is 0.210. And now if I square root both sides, I get and now it's only a matter of solving it algebraically, which you can use your GCSE math skills, and we get x is equal to 0.0373, and then we can sub that in for our moles of hydrogen bromide at equilibrium, which is 2x, so we get 0.0745. Alright, now we're finally onto the last chapter of the video. Oxidation is the loss of electrons. So for zinc, we'd start off with the zinc atom, and we'd form zinc 2+. And if you write down the charges for both sides, originally we have 0 here and a +2 on the right side. So to balance the charges, we need to add a -2 onto the right side. And the way we can add a -2 is by adding 2 electrons. So now the charges are balanced and the atoms are balanced. Reduction is the gain of electrons. So for chlorine, we start off with Cl2 and we gain an electron to form Cl-. And firstly we're going to balance out the atoms, and then we need to balance out the charges. So on the left side we have a charge of 0, and then on the right side we have a charge of -2. So I'm going to add -2 on the left side, and I do this by adding 2 electrons. So now the charge is -2 on both sides. All uncombined elements have an oxidation state of 0. The oxidation numbers of elements in a compound add up to 0. The oxidation numbers of the elements in a polyatomic ion, for example sulfate, add up to the overall ionic charge. So in this case, all of the oxidation states would add up to -2. The oxidation state of group 1 metals is +1. For group 2 it's +2. For aluminium it's +3. For hydrogen it's +1, but is -1 in metal hydrides. For fluorine it's -1. For the other halogens it's -1, except in compounds that contain oxygen and or fluorine. And for oxygen it's -2, except in compounds that contain fluorine, but in hydrogen peroxide it's also -1. So here's some examples for us to try. Sodium is in group 1, so it's going to be +1. Chlorine is in group 7, so it's going to be -1. Potassium is in group 1, so it's going to be +1. Oxygen is going to be -2. And then to work out Mn, we use the fact that the overall oxidation state is going to be 0. So we do +1 for the K, and then +x for the Mn, and then plus 4 lots of -2 for the oxygens, and then we let that equal to 0, and then we get X is equal to plus 7, so Mn is plus 7. And then for iron oxide, well, oxygen is going to be minus 2, and then iron, well, there's 2 ions, so we can label that 2X, and we have 3 lots of oxygen, and all of those are going to be minus 2 each, and altogether all of these oxidation states add up to 0, and then we can solve for X and we get, so iron is going to be positive 3, and then for the ammonium ion, well, hydrogen is going to be positive 1, so we have nitrogen, which we can label X, plus 4 lots of 1 is equal to the charge, which is plus 1, and then we get X is equal to minus 3, so nitrogen is minus 3. Alright, so that's how we work out the oxidation states of elements in compounds. Alright, so a reducing agent is an electron donor. And then an oxidizing agent is an electron acceptor. So for simple half equations, you write down the atoms or ions involved on each side, then you balance out the atoms, and then you balance the charges using the electrons. So here I've said to work out the half equations of the reduction of bromine and the oxidation of iodide, and then combine the equations. So for bromine, we start off with Br2, and if we're reducing it, we're going to gain an electron, so we get Br minus. And well, firstly we need to balance out the atoms, so we get 2Br on both sides. And then we need to balance out the charges, so I'm going to add 2 electrons onto the left side, so that both sides are minus 2. And for the oxidation of iodide, we start off with I minus, and we form iodine. So firstly I'm going to balance out the atoms, so we have 2I on both sides, and then I'm going to balance out the charges. So I'm going to add 2 electrons onto the right side, so that both sides are minus 2. And then if I combine the equations, I end up with alright, and then we have 2 electrons here and 2 electrons here, so they can just cancel each other out. So we end up with now preferably you want to be able to get to the stage where you can go from these 2 equations straight to this. You should be able to just recognize that these 2 electrons would cancel each other out. For complex half equations, you write down the atoms or ions involved on both sides. Then you balance out the atoms apart from oxygen and hydrogen. And then to balance out the oxygen, we add H2O. And then to balance out the H's, we add H+. And then finally we balance out the charges using electrons. So here we've got an example to try. Alright, so firstly, I noticed that we have 2 chromium atoms on the left side and 1 chromium atom on the right side. So I'm going to times this side by 2 so that we get 2 chromium atoms. So I'm just going to add a 2 here. And then we also have 7 oxygens here, whereas here we have 0 oxygens. So I'm going to add 7 oxygens. And the way we do this, instead of adding just oxygen, we add water when we're balancing out oxygen, like these rules that we said here. But now we have 14 lots of H's, right? So now we need to balance out the H's. And to balance out the H's, we add H+. So I'm going to add 14 lots of H+ here. So now we have 14 H's on both sides. And now I just need to balance out the charges. So the overall charge on the left side is 14 minus 2, and we get 12. And I got these numbers from the 14 lots of +1 and then the 2 minus. And on the right hand side we have 2 lots of 3 plus, and we get 6. So then to balance out the charges, I'm going to add 6 electrons to the left hand side, and now the charges are balanced and all the atoms are balanced. So this half equation is done. Alright, so this one's a lot easier. We have 1 Fe on either side, so we only need to balance out the charges. So here we have a plus 2, and here we have a plus 3. So I'm going to take away 1 on this side so that we can get a plus 2, and then I'm going to add an electron to signify that minus 1. So to combine the half equations, what we do is make sure that the number of electrons on both equations are the same. So for the top equation we get and for the bottom reaction we get, okay, so the number of electrons currently are different. We have 6 here and we have 1 here. But to make them the same, all we need to do is times the bottom one by 6. So now we have 6 electrons in both reactions, and they'll cancel each other out. So our overall reaction is alright, hope you guys enjoyed this video. If you did, make sure you comment, like and subscribe, and stay tuned for the next one.